Welcome. In today's discussion, we include the time response specifications of a second order system and the error constants, the corresponding error constants. As we know that the second order system response is splitted into two parts, that is the transient response and steady state response. Let me take you back to the response, which is shown generally like this. Here, uh, when the system response enters in the acceptable range of the error, the time it takes to reach in this particular error is known as the response of transient, and after that it is called as a steady state response. This figure indicates that there are some terms which are concerned with the response, and those can be considered while designing the second order system so that the system response can be satisfactory. The terms which are including are it is called the delay time. See, in detail we'll see, but since this figure is displayed, so see that the first parameter, this is called the delay time. So this D stands for delay. Similar to this, there is a rise time. This R stands for rise. This TP, this P stands for peak time. MP is known to be overshoot, peak overshoot, and the one more parameter which is called as a settling time. This S stands for settling time here. So, and this is the corresponding output of the response, and here it is shown that one is the output. We can convert this into percentage. If it is calculated in percentage, this could be 100%, this is 105, this is 95, and so on, this is 50%. So let's see that in detail and how to calculate these time domain or time response specifications. These specifications refer to the performance indices of the step response of a system. The indices are qualitatively related to following factors. Those factors are how fast the system moves to follow the input, because it is expected in general that the system should reach to the desired value in the quickest time, in the smallest time, and should remain as a value of the required. How oscillative, but it won't happen because all number of parameters are responsible for getting the satisfactory or unsatisfactory results. But considering all those design parameters, once these are set and if the technical terms are maintained, then it is possible that the response of systems could be satisfactory. But without focusing on the parameters of system, one cannot achieve the satisfactory response. That is true. Now, second is how oscillating it is, and third is how long does it take to practically reach the final value. Final value is just now we saw that 1 or 100%, that could be a final value, or this is also called as a set point value. Various indices are not independent of each other. Does not mean when one is changed, the other has to change. This is the meaning of it. Now, very first time that we saw in the response is the delay time. This is called as a delay time TD. It is the time required for the response to reach 50% of the final value at first instance. So once we start the system response, getting the system response or sketching the system response, and once we start with 0%, and what is the time required for the system response to reach from 0% to 50%, this is called the delay time. We know that zeta is the damping factor and this is the frequency and damped natural frequency, And once we know these two frequencies, because the second order transfer function gives you these two values, so once these two values are known to us, one can find this, or we decide the what should be the acceptable delay time, mentioned it over here, and if this is the frequency mentioned, then zeta can be calculated, because zeta is most responsible for getting the satisfactory or unsatisfactory results. So zeta can be calculated with this. So this is the first parameter that we saw. Second, next parameter to the delay time is the time called as a rise time. It is the time required for the response to rise from 10% to 90% of the final value for the overdamped system. Please note this. Else, for underdamped system, this is the time required from 0% to 100%. So we saw that 50% when the time start changing, the response start changing with respect to time. When it reaches to 50%, that is called delay time. When it reaches to 100%, this is called rise time. But this is considered for underdamped system. But the system, when it is overdamped and is not going to cross the final value, then in that case the response time rise time can be calculated between 10% to 90% only. So now the mathematical expression for this is TR is equal to pi minus tan inverse under root 1 minus zeta square divided by zeta upon, this is also called damped natural frequency. This is the combination omega n into under root 1 minus zeta square. This is the damped natural frequency. So by the way, again, what we saw in the earlier case, that first of all calculate, substitute what is the system zeta and omega n value, and calculate TR. When we are not satisfactory, just mention this value and accordingly find out the zeta, and that should definitely give us the satisfactory result. So next parameter to the rise time is the peak time, called as the TP. It is the time required for the system response to reach the peak value of the time response. So the first peak value of it is shown, and that is called a peak time, and this is pi by omega d, and it is again calculated either first of all sketching this, and if not satisfactory, change the value of zeta, so then the t can be made satisfactory. Two more parameters are left which are concerned with the time response specifications of a second order system. The peak overshoot, it is the normalized difference between the peak value of time response and the steady state. We just saw that when the first peak we get, the there will be difference between our desired value and the response which is shown by the system. The difference is known as a peak overshoot, and here in the mathematical expression also, the output at peak time minus the maximum output which is shown, it is nothing but the peak time. And for second order system, it is mentioned in terms of, this is the formula which shows that what is the relation between zeta, and please note that this is the term which is not including omega n, that is undamped natural frequency. So this is calculated in percentage because we have here multiplication with 100. And the last parameter, which is the settling time. Settling time is the time required for the system response to reach and stay within the specified. So once the transient response is over, then system is going to enter in the steady state. So what is the time required by the system to reach into the steady state response or steady state zone? This is called the settling time. And probably as mentioned that when I mentioned that it is in the acceptable range or variable error, that error value could be plus minus 2% or 5% of it. So once it reaches to that value, then we say that the system has been reached to steady state response, and the settling time is calculated with this formula, mathematical relation. This is 4 by zeta omega n. Please note that MP and TS are not defined for overdamped and critically damped systems. Now, this we already saw this is the response of this, and once again see that this is the way to know that this is the peak overshoot difference between this desired value and the peak value, and these are the corresponding parameters. So now when this is system response plotted, there are some parameters which can be analyzed to know that what is the quality of the response or quality of this control system, and that is nothing but by knowing the steady state error. So ESS stands for steady state and E stands for error. So it is the error between actual output and the desired output when time goes to infinity. So it is the steady state error. This is the time when it tends to infinity, and now this error is nothing but, as mentioned in the definition, that is the difference between actual output and the desired output. So it can be simplified and then into S. So S into S will be the Laplace form, and then this S up into Rs upon 1 plus Gs. This is the relation of steady state error, and we can substitute the values of different inputs. Rs equal to 1 by S, then ramp input, parabolic input, impulse input, etc., and the corresponding steady state error value can be calculated. So it is possible to calculate the steady state error for different types of inputs, because the formula is, this standard formula is with us. And now let's have the unit step input, for which we know that Rs value is 1 over S. So substituting here, we are going to get the steady state error is equal to 1 upon 1 plus Kp. So this Gs is equal to, because we do not know what is the value of terms in this S, so and hence it cannot be considered as 0. So Gs is equal to Kp. So where Kp is equal to limit S to, so substituting S is equal to 0 in the Gs equation or Gs value, say one can find out the Kp value. When it is cancelled, then you can say that it is going to be 0 and the steady state error is going to be 1. Now when ramp input is applied, then it is 1 over S square, the steady state error accordingly it will be 1 over Kv. So now see, the case is that, like, if it happens like in this case, it will be 0 and then it will be infinite. So this is what the change is. Now we are noting that when it is a unit step and unit ramp, the terms, this simple term 1 plus Kp is going to give you this one value, but here it will give you error as a infinite. And it is to be noted that when velocity error is not error in the velocity, but it is the error in position due to ramp input. The third input when applied, it is the parabolic input, substituting R is equal to 1 over S cube in the equation, and we are going to get similar to the earlier. Is it was Kv, V stands for velocity, and this A stands for acceleration. So acceleration error constant is calculated with limit S tends to 0, S square into Gs. So the error constants Kp, Kv, Ka describe the ability of a system to reduce or eliminate steady state errors. These values mostly depend on the type of system. When the type of system increases, the steady state error decreases. These are the features of steady state error. Steady state error is a measure of system accuracy. Ideally, the system should match the reference input as time progresses. Steady state error should be as low as possible. ESS, that is steady state error, depends on the reference input Rs value. Just now we saw that we have 3 formulation, and the type of system Gs, because that is responsible when or the term that includes, when more of the terms of S, then it is going to do cancellation, and the reflection of this will be there as a steady state. And steady state errors are calculated only for closed loop stable systems. Now these are the type of feedback systems mentioned in the time constant form, in the pole 0 form. So when is a time constant form, it will be tau z. Since this is a time constant of 0, this is the another 0, time constant of another 0, and so on. And this is the type of system that is going to mention S to the power n, The power of this n will decide the type of system. When n is equal to 0, we can say the type 0 system, 1, 2, 3 when n increases that way. And the another way the transfer function can be expressed is the pole 0 form. So it will be the term, and there is will be no coefficient with this s, and this is expressed as s plus z1, s plus z2, and so on. So the time constant form can be converted into this, or this can be converted into time, and that's why the time sorry, the gain which was shown as k is going to change with k dash, and it is not k, because once we alter this equation in this form, the k is going to change and the new k will be there, and that is known as k dash. S raised to n indicates the number of poles at origin called as type n system. As s is equal to 0, s to the power n term dominates in the determine the steady state error. So for let's see now what is the when time 0 system is there, type 0 system, and the corresponding steady state errors. When it is a type 0 system, there will be no power of s, and so this will be the transfer function in the pole 0 form. Substituting all these values here, because we know that what is the gs, and this gs equation is taken into this all steady state errors and corresponding equations. So it is observed that for type 0 system there is a specific value of steady state error, but the velocity steady state error and acceleration errors both are infinite for type 0 system. So it is very clear, and it is the only time that is non-zero or non-infinite, and that depends on value of kp. So it is called as a the position error constants. So for type 1 system, when n is equal to 1, then see that it is going to say, that means type of the system affect the steady state error. This is what the conclusion in short. Steady state error position, definitely for type 1 system position error is going to be 0, but for type 1 system the velocity error is going to be 1 over kv, and this now it remains as infinite. So see that initially it was some specific value with the position error, and the two, that is this steady state error for velocity and acceleration, both were infinite. Now for the type 1 system, this has been made 0, this is specific value and it is infinite. Now let's see the last slide, that where what is the response or what is the value of a steady state error for type 2 system. Now it is shown that type 2 system, so when type goes on increasing, the error goes on reducing. This is what the sentence which is written, and it is now confirmed. So when this is the case, now the last error which remains is the acceleration error. For type 2 system, the third error, there is going to be some new specific value, and the position and velocity errors are going to be 0. So this is all about the time response specifications and steady state error. Thank you.